decision-making community wants from us as glaciologists is to be able to say, well, what's going on with the sea level budget? Tell me how big to build this levee by 2100 so that I don't overspend or underspend on it, and so that we can minimize the costs of dealing with this problem. So this is from Wonderground, and I just like the schematic of the human body standing there. And it projects sea level rise out to 2100, and the errors go from the bottom of the dark blue one to the top of the light blue curve. So basically what you see is, yeah, we have a pretty good handle on measuring sea level change, but we can't predict it out into the future to save our lives. And so the question is, why? If we can make measurements of glacier mass budgets, why can't we predict how sea level is going to change? And so is it the temperatures? Do we just not understand what's happening with temperature? And is, some region, or the glaciarized regions, changing their temperature faster than others? And so these figures, I think you could argue that you get some traction from that argument, but it certainly can't explain the whole story. There has to be more going on. There's this gorilla that's been sleeping in the corner that we've been wanting to ignore, and we can't do it anymore. And that gorilla is ice dynamics. And this is really, really nicely illustrated by the Chugach range. This is a DEM difference done by Etienne Berthier of the whole Chugach range from the late 1950s to 2007. Blue is mass gain, red is mass loss or volume change. You see this big red bullseye over Columbia Glacier, which talks directly to the ocean. And it's got a neighboring tidewater glacier, Harvard Glacier, which is blue. It's been gaining mass. They're clearly in the same climate. So you can't invoke temperatures to explain these. Columbia Glacier's accounting for about half the mass loss from this whole mountain range. So again, it's disproportionately important. And we don't have a clue what's going on, but we're starting to realize that, hey, these are important. So why are they important? How could this process of ice dynamics, why is it so important, and why have we ignored it? So this is cool video footage from Jakobshavn in Greenland. I'm showing it not because it's relevant to Alaska, well, it is relevant to Alaska, but it's dramatic and it's nice footage taken by the Extreme Ice Survey. So the scale of this is you're seeing these icebergs are probably about 100 meters tall, and the width of the screen is on the kilometer length scales. So this is instantaneous transfer of mass from terrestrial storage to the sea. This is big, big mass transfer. This is the biggest canoe paddle in the ocean. The physical oceanographers are like, wow, this kind of mixing doesn't happen any other way. But this isn't just the stagnant disintegration of these glaciers. There's feedbacks and couplings. And that's what I want to show you next, but it's worth watching the rest of this little video. And these are huge. That iceberg is a couple kilometers across. So this is like Manhattan going out into the ocean real quick. So this is what is important. And imagine trying to study this, trying to put instruments or sensors in this environment. You can't do it. So that's part of it. So if we return to this is formally how we study the mass balance of glaciers. These complicated terms over on the right are the dynamic terms. This one that's on top of the word surface balance is the slowly changing term that we've wanted to pay attention to, in part because it's easy. But there's all these couplings and feedbacks that are nonlinear between the calving, the thinning rates of the glaciers, and the ice flow. And this is really nicely illustrated at Columbia Glacier. This is a picture a day since 2004 from Columbia Glacier. The camera keeps rotating as the glacier retreats. But you can see the thinning. You can see the forward flow. We've got about 100 feet a day of forward motion of the ice. And you can see the change in the terminus position from calving. So this process is happening fast. It's not this slow turtle thing that people typically think of as how glaciers work. This is a real dynamic process. And it's got all these nonlinear feedbacks. The ocean is involved, the atmosphere is involved, and we don't know how to get a handle on it yet. And that's why we don't have the ability to really get at sea level rise yet. So here's Columbia this is 1979 Austin Post photography. Here it is in 1993. Here it is in 2004. The terminus there is about 2.5 kilometers wide. Here it is in 2010. So major changes in the length, 50% reduction in ice thickness, and the whole time you're pushing ice at 25 meters a day at the terminus out into the ocean. Normal glaciers flow at about 30 centimeters a day. So this is a major, major speed up thing. It's a big conveyor belt. So back to the sea level thing. Why the uncertainty when we look forward? Because of this ice dynamics thing. It happens quickly. The calving glaciers can turn on tomorrow or turn off. We're not able to predict that. And so the way that we've been projecting these things, and everybody wants it to 2100, is we just use these physically based mathematical deterministic models that have these rules. If A happens, then do B. And so far, the IPCC estimates are totally excluding dynamics because the consensus is that we don't have the equations to govern the physics. But we know they're happening. So how far out can we go? Do we have anything besides extrapolation? So in this figure on the left, the red little bars at 2100 are the IPCC estimates. And then the blue and the gray are sort of more extrapolation. So what's happening today, what if it happens out into the future? What if it goes faster? That's why all the uncertainty, because we don't know if these things are going to turn on or turn off.